bet you guys can hear me now. I see the indicator light bouncing. However, I'm willing to bet that the audio quality is suddenly very different than it normally is. Like, do I sound different than I normally do?
Yeah, kind of.
Better or worse?
A little worse, but it's.
Yeah, I figured, because what I did was, this is the microphone built into the camera, not the microphone built into my laptop. Let me see if changing back fixes it.
I mean, we can still hear you. It's fine.
Okay, I switched it back to the microphone array in the laptop, so now it's working. That's weird. It's probably because I've been messing around with my laptop a bunch. I've been streaming a bunch of games when I'm not in class. So I'm sure switching between this and OBS and my video capture card and stuff, it's probably not the best for the drivers. Anyway, what was the addition? Okay, I have no idea how much of my preamble you guys heard. I just have to start over. Yesterday, we talked a little bit about the multiplication principle, and that is the notion that if you want to combine multiple events to figure out how many combined possible events there are, all we do is multiply. So that is to say, yesterday when we talked about, well, what could happen if you roll 2 dice and you look at the total, right? Technically speaking, by the multiplication principle, yes, there are 36 different outcomes, but what is the deal with those 36 different outcomes? What makes that a harder problem to think about? Anybody? Sure, you roll 2 dice and you get a sum, and there are 36 events because it's 6 by 6. But what makes it more complicated to think about that possibility?
You can get the same sum several times. Like, for
Right.
example, you can get like 7 the most time.
Correct, yeah. So we kind of drew out a Punnett square type device, right, that grid. And we talked about what the possible outcomes are of the sum. And because there are repetitions within those sums, of the 36 possible outcomes, not all of the 36 outcomes are distinct. So this multiplication principle does figure out the possible, the total possible events. However, since getting the sum requires adding them up, there's only one way to make 2 here, but there are 2 ways to make 3, 3 ways to make 4, 4 ways to make 5, 5 ways to make 6, 6 ways to make 7, blah, 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 blah. So actually counting them up would require some more complicated counting scheme. The multiplication principle is only capable of capturing very, very, very basic information. The rest is kind of up to you and your own logical routine. So please consider the following warm-up question that uses the multiplication principle. A man has 8 dress shirts, 3 jackets, 3 pants, 4 ties, 2 shoes, and 2 belts. How many possible suits exist within this wardrobe necessarily? And this is ignoring all of the fun parts of suiting, like pocket squares and lapel flowers. And then item number 2, let's go ahead and add the additional rule. And this is where we get outside of the multiplication rule and you have to like actually start doing some slightly harder thinking. Suppose that this gentleman doesn't want to mix together pants and jackets, so he keeps those together, right? That is to say that these 3 pants and these 3 jackets, let's say it's black, gray, blue, they actually came together and he doesn't want to mix that. So let's say that he doesn't want to mix suit colors, and he also doesn't want to mix together leathers, which is to say 2 shoes, 2 belts. This is probably 1 black belt, 1 brown belt, 1 black shoe, 1 brown shoe. Let's say that you don't want to mix those either. So by enforcing those rules on this wardrobe, how many less suits are now possible? So item 1, figure out all of the numbers of combinations up here. Item 2, figure out the numbers of combinations over here. And then we will get going with today's notes. Today we'll learn about some new buttons on our calculator. Oh, also I mentioned that we need to take a class picture. I'm super sorry, but I'm gonna ask everybody to like turn your webcams on real quick. I said this yesterday at the top to be kind of photographically presentable today. So if you have a quick moment to all line up, let's take 60 seconds to do this, no more. Let's get this done so that we can be in the yearbook. What up? Usually that's extremely reductionist, like to talk about how Thomas Edison invented the light bulb totally ignores the fact that that guy was mostly a CEO. He was mostly running a business. The actual scientists who discovered the technology to make the light bulb necessary, their names are lost to history because of licensing agreements and whatnot. And on top of that, to attribute all of that to a single person is to ignore the 150 years of technological development leading up to that moment, you know? So it's actually really rare that in history you could be like, hey, this one thing was started by this one dude, right? However, with men's suits, you can actually like point a finger and be like, it was this guy. And the dude's name is Beau Rummel. And he is a late 1700s figure. And he is basically single-handedly responsible for inventing the men's suit and getting people in England away from dressing like kings. Like back in the day, people in Parliament would dress in powdered faces and powdered wigs and robes and all that like wildness. He was the first dude to just wear a suit, like white shirt, riding jacket, skinny pants, dress shoes. And he was so popular and famous that from his influence, that's what kind of leads to the reformation of men's fashion in that direction. Weird stuff. Anyway, let's go ahead and talk about this.
Wait, Mr. Robinson, was he like a king or something?
No, he was actually, and for more information on this, I would like to recommend a podcast, because the story that I'm about to tell you is straight from a podcast, but it's like a well-researched one. Within a podcast called 99% Invisible, which is just a really good design podcast, I would check it out if I were you. It's excellent stuff. But within this podcast, there is a sub-podcast called Articles of Interest, which is just stories about fashion. Even if you don't like fashion, that might sound, if you don't like fashion, that might sound boring. I guarantee every episode of Articles of Interest is generally interesting, mostly because you can't really tell what they're about until they're 3/4 of the way through. They just have really good setups or whatever. He was actually the son of a secretary of a prime minister. And the secretary of the prime minister back then did a bunch of embezzling, which took his family from being working class to being aristocratic, because that's what it actually takes to be in the ruling class, is just have the money. And then after his parents died, he became in charge of the whole fortune. So he was just like a celebrity rich guy, the same way how we have those today. Like people who don't actually do anything, but they're just rich and influential because they're rich, you know?
Right.
The dude just went around London being like a dick and insulting people and being fashionable. And he kind of had a cult of dudes who wanted to be like him and dress like him. And that's what led to the widespread wearing of the suit through British aristocracy. And then that goes out to the rest of culture.
Interesting.
Yeah, wacky stuff. Wacky stuff. Okay. So let's go ahead and go through this. So item number one, how many suits are possible within this wardrobe?
1,152.
And how is that arrived at?
Just multiply all the, combinations.
Yeah, so this is just straight up multiplication principle. If you want to know how many possible combinations exist within a set of elements that you are combining, all we do is we multiply them. So this is to say that 8 times 3 times 3 times 4 times 2 times 2 is 1,152 possible suits, though that doesn't guarantee that all of them are good suits, right? One can totally get away with mixing jackets and pants as long as you do it right. But there are other rules that need to be enforced that are a little bit more arbitrary. Things like probably don't wear a patterned suit with a patterned shirt. Like it's a lot to wear a striped shirt with a striped tie. So while this is definitely, this is the correct mathematical answer, they're probably not all good. And then item number 2, we enforce some extra arbitrary rules on here, and this is going to decrease our combinations, right? So what is that going to do? How many less combinations are there? What would be a good way to figure this out? So my argument here, the easiest way to figure out the answer to this question is to just reduce the parameters here that we're multiplying together. So it is 8 dress shirts, but instead of saying 3 jackets and 3 pants, which the product here gives us 9 combinations of jacket and pant, what am I going to reduce this parameter down to?
6?
No,
3
even less than that.
jackets. 3.
Just 3. And I'm going to say that this is 3 suits. Because if we're not matching jackets and pants, right, if you can't wear a black jacket with brown or with blue pants, then this is going to reduce it down to just 3 suits if we're being forced to match. One other pair of parameters here is going to be reduced down by our tastes in fashion. What other parameters?
The shoes and the belt.
The shoes and the belt. So instead of saying 2 shoes and 2 belts, which don't mix leathers unless you know what you're doing or you are wearing one thing which contains mixed leather. Like I used to have a pair of dress shoes that were both brown and black. With those you can wear any belt you want, but usually if you have a brown belt, brown shoes, black belt, black shoes. Anyway, 2 full sets of leathers. Then instead of just taking the product down this row, now it's going to be 8 times 3 times 4 times 2. And so you'll notice this reduces it suddenly way down to how many?
192.
Just 192 suits. And so to get how many less it is, we subtract the 2. And so suddenly, simply by enforcing these 2 rules on the set, there is suddenly 960 less possible suits as to compared when we're getting dressed, I guess, blind, right? Like if you were to just go in the closet and put on whatever. Is that warm-up question okay? So the point here that I'm trying to get at is the fact that once you start removing possibilities from a set of elements, or you start enforcing additional rules like this, which reduce down our parameters, you get a very, very rapid deduction in number of possibilities. If you allow yourself to wear any combination of junk that makes up a suit, more than 1,000, but by enforcing these 2 simple rules, right, that we're gonna keep shoes and belts together and that we're gonna keep jackets and pants together, this suddenly takes us down to 192 suits. Is this okay?
Mr. Robinson, I have a quick question. What if you're combining 2 parts that are not equal? Like, let's say we had 4 jackets and 3 pants. How would you combine that?
There would be no good way to do that because you would have to say, well, there would be a way to do that, but it would be based on whatever rule you would come up with if you had 3 jackets and 4 pants. So if you had no rule, if you were like, okay, still just combinations, and that would just be 3 times 4, which gives you 12 combinations of jacket pant combinations. But within that, if you were to enforce some sort of additional rule using the word or, there is a way that we can do that mathematically, but it would be more complicated and we won't have the vocabulary to do that until next section.
Okay.
But we will get there being like, well, what if I kept my black jacket and my black pants together, but I allowed myself to mix together a brown jacket, a blue jacket with brown pants and blue pants? So if you have that either or setup, you could do that with math, but it's a little bit more complicated than this. It would require factorials.
Okay.
Good.
Got it.
Okay. So today what we're going to get into is we're going to get into various counting equations for some different scenarios. And like always, sorry, let me just check one thing. And this is a lesson that actually comes with, there we go, okay. That comes with some new calculator buttons. So as part of today's notes, we'll be taking a look at the calculator emulators that I have. So I would recommend that if you have a TI-84 with you, that you bust it out. Also, these calculator buttons are present on scientific calculators if you still have or use one of those that you like. That's fine. Okay. So today we'll be continuing the notes on section 5. Today we'll be talking about counting principles. Okay. Student folders. Okay. All right. Okay. So let's go ahead and start off today. And for whatever reason, I always find that this stuff is easier to explain with examples rather than to try and prove it with pure math, right? Let's say that we are attempting to choose we want to choose a team of 3 students from our class to compete in a math contest. And we are going to do this, I guess, fairly randomly. But the deal with this math contest is that the team of 3 that we are sending out, not all of the roles in the team are necessarily equal. The 3 positions, right, the roles in the contest, is that there is some first role, person 1 being the captain, just kind of the person who's in charge of everything. Person number 2 being the researcher. And then person 3 being the modeler. So the person who's using software in order to try and model out the answers that they might propose to the problem presented by this math contest. The reason why this is important, why there are different roles, is that one condition that we'll be looking for when it comes to applying these counting principles and these counting equations is the question whether or not order matters. And in this case, the point of assigning roles is so that order will matter, order matters. That is to say, changing the order of the elements that we are about to talk about will change whether or not this counts as a unique possibility. This is to say that if we were to use some sort of random number generator in order to build out one possible team, and this first possible team would be captain is Susie, researcher is Alice, and then the modeler is Alex. Then if we were to run this back, right, if we were to say, okay, random number generator, give us another possible team, that even though it were to select the same 3 people, Alice, then Susie, then Alex, that even though there's only a single swap in here, this possible first team combination and this second possible team combination, these 2 are different. Only because when the order matters, in this first team, Susie is the captain, Alice is the researcher. And in the second team, Alice is the captain, Susie is the researcher. So even though it's the same cluster of 3 human beings, the order in which they were selected makes this particular outcome different. Is this okay?
Yeah.
Yeah, right.
In these types of scenarios where order matters, we refer to these as permutations. Permutations. Oh, I don't normally put vocab in quotes. Let's not start now in the last week of school. Nonetheless, permutations are counting scenarios where the ordering of elements changes whether or not that set is unique. In this case, because this team has particular roles to it, this has to be considered a permutation, because just changing the order of two of the elements changes whether or not that secondary team counts as being unique and will add to our total. So do y'all know off the top of your head how many people are in this class, or is it just me because I'm the teacher and I take roll?
I have no idea. I think like 23 or 4, I think.
23 is correct. So if there
Yeah.
are 23 people in the class, when we build out this team, let's figure out how many different teams could we send to this math competition, right? So how many teams? Of 23 students. So the number of teams of this form can easily be calculated out using the counting principle. How many different students do we have that can fulfill the captain role?
23.
Yeah, so for that first role, it's going to be just 23. And then how many people could be in that second role? How many researchers could we have?
23.
I'm going to go ahead and say not 23, because if I select you to be the captain, you also can't be the researcher.
22.
22.
Mr. Robinson,
22.
doesn't the same apply for the teams though? Like there's one person that's going to be a captain, so then
Yes.
therefore can't be a researcher or a modeler.
Correct.
Yes.
So when we choose the captain, there's 23 students in the bucket. I pick one captain, and now when it comes to choosing the researcher, I have 22 students who can be the researcher because one was already chosen as the captain. So now how many people could we choose to be the modeler?
21.
21.
I see.
Drop my pen. Times 21. Oh boy, I saw a meme of somebody, like this big pile of broken glass with a computer monitor in it and a desktop computer in it. Like the person had their computer set up on a glass desk. The glass shattered, and not only did it destroy the desk, but everything fell through because it was glass, right? If you can't tell, I'm sitting here at a glass desk, and ever since I've seen that, I have been paranoid about accidentally shattering the surface of one of my desks and just spilling my computer on the ground. While we're all stuck at home with COVID and computer components are extra expensive and hard to come by. Random thought. Nonetheless, this here will straight up calculate the total number of teams with no ambiguity. It's straightforward application of the multiplication principle. And so if you do this, right, you get 23 times 22 times 21, which is to say that of our class, there are 10,626 possible unique teams of just picking out 3 of y'all to send to a math contest. Now, this is nifty. However, what we want to be able to do is we want to be able to write out a formula which does this for us. And here is that permutation formulation. You'll see this written a couple ways. The formal way to write this with statistics would be to say P of n comma r. This is a type of function, sort of. It doesn't meet all the criteria of a function, but you can think of it that way. Or another shorthand you will see for this idea for counting up permutations is n PR, which would be read out as of n elements, please permute r of them But here is the deal. Here is what this is doing. NPR is equal to N. And actually, before I just give it to you, what does this look like to take a number and multiply by a number that is smaller, 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 smaller?
Factorials.
This is some sort of factorial notion here. And so the way that we get our permutation formulation is to say, well, the top is going to be n factorial because I want you to multiply by 23 to 22 to 21, da 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 da, all the way down. And so we start off by saying n factorial, because if I did 23 factorial here, it would give us 23, 22, 21. But to cut off the rest of the digits to say stop multiplying after 21, then in the denominator we have n minus r factorial. So down here we would do 21 minus the number of things that we are selecting, 21 minus 3, right? And then in that denominator, that would give us 20 factorial, 23 factorial divided by 20 factorial, chops off the rest of those chasing digits. So on one hand, this is a formula worth knowing, but on the other hand, this is built into all calculators because this is one of the fundamental building blocks of statistics. And so if we wanted to get back this exact same number, right, by those methods, everybody bust out your graphing calculators, please. What we're going to do here is underneath the math menu. So number one, turn my calculator on. Number two, go to the math menu. You'll see here that on the math menu, if you either go 1 to the left or 2 to the right, you end up over here in the top right, which is PRB. This is the probability math menu. This is where we find our command for the factorial, but we also see option 2 here is NPR. So I'm going to go ahead and select that. Now, before you plug anything into NPR, NPR actually needs 2 digits in order to work. And so you need to first plug in 1 digit for N, select NPR, and then plug in your digit for R. So in this scenario, before I select it, I have to type in 23 because there's 23 students in the class that we're selecting from. Then I go to math, probability, NPR. And of those 23 students, we're building out unique teams of 3. I'm going to hit enter. And that also gives us back exactly 10,626. Is this first item okay?
Yeah, sounds good.
Cool. Okay. So that's first fundamental page of notes, number 1, permutations. And now to take this example kind of to its next level or whatever, let's go ahead and change the rules of the competition. So for example 2 here, we are still talking about a math competition. However, in this second set, we consider a different math competition. However, in this second math competition, the teams do not have defined roles. So this is to say that of our team, the team is just members 1, 2, 3. And here, the logical distinction that I want to draw is that in this case, the order does not matter. That's always the logical test that you want to use to try and separate whether or not we are talking about a combination or a permutation. We are simply asking ourselves whether or not the order matters or the order does not matter. So this means that, to draw the distinction with what we were talking about before, right? This is to say that if we were to do this by a random number generator, and Susie were to be chosen first, then followed by Alice, then followed by Alex, and then we were to subject this to a random number generator, and the second time it were to pull Alice, then Susie, then Alex, that these two teams are identical. These both count as 1. In cases where the order does not matter, right, these two things, which would have been distinct underneath the rules of underneath the rules of permutation, they counted as 2 separate events, and so that equation will count both of them as being separate. In this case, where there are no distinct roles, and therefore the order in which the students are chosen, right, that does not matter, this is what we refer to as combinations. Combinations are counting scenarios which are agnostic to selection order. And so, do you think this number of possible teams selected from the class, should this be bigger or smaller than what we calculated last time?
Much smaller, right?
It should be much smaller because this is saying that we want to go back through our old answer and we want to remove any duplicates, right? We want to remove any 2 teams which are identical to each other by the number or by the people in them, but only differ by the order in which they were selected. And so the combination equation is harder to describe or figure out using just the basic counting formulas, which is why we go over permutations first. That one I think is the most straightforward to relate to the multiplication principle. But when it comes to calculating combinations, again, we have some formalities. So in college statistics, you'll probably see it this way. So combinations of n elements of size r, which would be the same here as n elements combined in sets of r. This is exactly the same as the permutation equation, almost. This is going to be n factorial divided then by n minus r factorial. But what this removes out is an extra term which defines the number of repeated sets, and that is r factorial. The main difference here is that we are going to divide out r factorial, because dividing out r factorial, that different term right here, this will remove repeated sets. How this works is that in this scenario that I've set up to explain all of these ideas, we're choosing teams of 3. And by the rules of maths, if you were just talking about, well, how many different ways can I build out this team of 3, considering this team of 3 is Susie, Alice, and Alex? This right here is going to be 3 factorial itself, which is equal to 3 times 2 times 1. This is the number of ways that you could order one team of just Susie, Alice, and Alex. And again, I think that that is a pretty straightforward idea on its own, because if you ask yourself, how many ways can I put these 3 names in order? Well, there are 3 names I could put first. I put a name first. Now there's 2 names I can put second. And now there's only 1 name I can put down below. So that is to say that of the unique team, Alice, Susie, and Alex, there are 6 different ways I can put them in order. So down below, when it comes to our calculation or whatever, we are dividing the number of permutations by 6 because it's removing those repeated sets of 6. Again, this will now give us a way to calculate out the number of possible teams that we could select from our class of 23 students. So once more, let's go back to our calculator. Same deal as before. It's going to be 23. Then I click math, and then I go over here to probability. Under the probability menu, I go down to option 3, which is NCR. So of 23 elements, how many different ways can I combine 3 of them into unique sets? And that gives me 1,771 different teams. So in this case, and we would write this way, C of 23, 3, which would be the same as 23, combine them into 3, which would be the same as 23 factorial divided by 3 factorial times 23 minus 3 quantity factorial. This is equal to, I already forgot, 1,771 possible teams. Is that okay?
Yep.
Yeah, okay. So those are the big ones. I got 2 other really small, oh, I'm sorry. Yeah, I have 2 more small notes that I want to make of ways that we could modify or flavor these 2 counting equations in order to make them a little bit more useful. Yeah. Yeah. Beware repeated elements in permutations. Be very careful when it comes to counting up permutations if you have repetitions within that set of permuted objects, right? So just kind of to draw an example by contrast. How many ways can I rearrange the letters in pens? So how many different ways can I rearrange the letters in pens in order to make additional letters? Also known as a Scrabble question. This is a pretty standard like statistics type question of like, I have these Scrabble tiles. How many words do I have to check in my head to know all of the possible things that I could play, right? So what is this asking us about? How could we calculate this, or how could we reason this out? So what I'm saying is, if I have 4 letters, P, E, N, S, pens, right? That 1, I can spell out, obviously, pens. That's my first one. And then number 2, I could also spell out spen. I could also spell out neps. I could also spell out ESPN. How many of those are there? So let's think about it this way. Hard and fast, ask yourself the question, does the order matter, yes or no?
No, because you're just asking to change the letters, right? So no.
I would say the order is everything. Actually, nothing matters other than the order. That's what I'm changing. I'm changing the order of the letters.
Okay. But they don't have to be like actual words, right? No.
No, this is math, not English.
Right.
Yeah, I'm not asking you how many words can I get by rearranging this. I'm asking how many ways can I rearrange it.
So,
That is
Mr.
to
Robert,
say that if you were
it
playing
16?
Scrabble, hold on, that if you were playing Scrabble and this was your hand, how many words, how many blurbs do you have to check for actual words? You'd have to think about all of these, looking for ones that would be valid plays. And what's the question? Alex, you had a question and then I cut you off?
If the order doesn't matter, so you're taking 4 times 4? Because there's 4 spots and there's 4 letters.
No, I actually think that would give you a overestimate. I would think of it this way. Put all 4 of the letters into a bag. How many letters can be in that first position?
4,
How many letters can be in the second position?
3.
How many
3,
letters can be in the third position?
2, and then
2.
1. That makes sense.
Correct, yep. So you could just say that the number of ways here that this could be done out, well, this would just be 4 times 3 times 2 times 1, which is going to be equal to 4 factorial, which is 24. So there's 24 different things that you would have to check for wordiness to like have a well-formulated move in Scrabble made up. However, the way that you guys want to use those permutation and combination equations is by asking yourself the following. Does the order matter? If the answer to that question is yes, you're using the permutation equation. Does the order not matter? If the answer is no, you're using the combination equation. So by realizing that the thing that actually matters here, well, that is the order. That means we're in permutation land. And how many elements am I playing with? How many things are here?
4.
Sorry?
There's 4 elements.
And how many of them are we using to spell out any given word?
4 factorial.
We are using 4 of them. And so if you
4.
want to use the permutation equation, simply put, this is 4p4. I have 4 elements and I want permutations of all 4 of them. This will also give you 24 if you use your calculator, and the reason why this works is that in terms of the actual permutation equation, this is 4 factorial, then divided by 4 minus 4 factorial. 0 factorial is equal to 1. And so this is just 4 factorial divided by 1, which is also equal equivalently to 24. However, the one wrinkle that can mess up our fun when it comes to a permutation is what happens when there are repeated elements. This is to say, for example, how many ways can I rearrange the letters in, and give me 1 second. I don't want to spell this wrong. All right, yeah, I'm not done. How many ways can I rearrange the letters in Mississippi?
Good one. Good word.
Yeah, this is the classic, simply because it is too big of a value for you to figure out straightforwardly, right? And here's why this produces for us a huge complication to our scheme, right? Let's go ahead and say that when we start counting this out, this is our first entry, right? Item 1, Mississippi. That's number 1. We might as well count that first. That's obvious.
And Mr. Robinson, do all the S's count as separate letters or one letter?
That's a hell of a question, and that's exactly why I bring this up, is to answer that problem. So let's go ahead and color code this S as being yellow, and I'll color code this other S over here as being blue. If I were to quote unquote create a different word by swapping those two, so that my second word is actually MISSISSIPPI. Now the blue S is over here, and the yellow S is over here. Is this actually a different word?
No, same word.
No. So you'll notice here that of these, I think it's 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, 11. Of these 11 letters, right? Swapping these two is not actually going to give us a different word. It's going to give us back the exact same word. So when counting these out, this doesn't count, right? The repeated elements, which in this case S, remove possibilities. That is to say that if you were to give me the answer 11 factorial, like it was up above, this number is too big because of these repetitions. Typically, when it comes to counting permutations in cases where you might have repeated elements of the set, we have a special formulation just for this. This was going to be n factorial divided by r1 factorial times r2 factorial times r3 factorial, dot, 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 where down here in the denominator, these r factorials, r sub n factorial, these represent repeated element counts. And where this right here is our permutation counter, permutations with repetitions. Also a classic thing to have to deal with in basic statistics. So this is to say that if you had 11 elements and you were working on permuting them, then your count would be huge. It would be 39 million different words that you could rearrange out of the letters in Mississippi. However, what this is saying, this permutation with repetition, is that we're going to start with that number. We're going to start with 11 factorial. But because swapping two S's or swapping two I's or swapping two P's, because that doesn't actually produce a brand new term, right? We need to divide all of those repetitions out. And so in this case up here, we're going to get 11 factorial, and then we're going to have to divide out the count of each one. Now, I think one elegant thing about this is that you're actually always doing this. But for m, since m is unique, that is just going to contribute a 1 factorial. And what is 1 factorial?
1.
1. It doesn't change anything. Dividing by 1 does not matter. So you can ignore anything which is unique. So I'm not going to include the m. It would just be a 1 factorial. But what about I? How many times does I occur here?
4.
It occurs 4 times, which is to say that in just considering the arrangement of i's, 4 times 3 times 2 times 1 will tell us how many ways we could swap around I without moving any of the other letters. So because I is repeated, I got to remove 4 factorial from the denominator. So this is 4 factorial for I. And then S is also repeated. I need to remove out the repetitions there. How many times does S occur? It also occurs 4 times. So I have to divide out a 4 factorial for that S. And then are there any other repeated elements?
Papa, P.
P. And it only occurs 2 times. So for that, I have to divide out a 2 factorial to get rid of P. And like I said, technically, if you want to include it, there's also a 1 factorial for here for m, but of course, this doesn't change the math of this scenario at all. You only have to divide out the repetitions. And so before, if I were to type in 11 factorial, I would get that this was 39,916,800 different combinations to consider. I'm sorry, not combinations, permutations. But because these elements are repeated, we'll have to divide them out. And so to get the correct answer, this is wrong, too big, I will now have to divide out the products of 4 factorial times 4 factorial times 2 factorial, which it's unnecessary for me to type in 2 factorial. Why? What's 2 factorial?
2.
It's just
yeah,
2. It's 2 times 1.
2.
But nonetheless, yo, check this out. Because of all of these repeated pieces, because of the reoccurrence of I 4 times, the reoccurrence of S 4 times, there's actually only 34,650 ways to permute the letters in the word Mississippi. So here is our equation for counting out permutations with repetitions, and why it's important, man. This is a huge reduction, suddenly down from 40 million-ish to 35,000-ish. Okay, so that is our primer on counting principles. Principle 1, the multiplication principle. That is to say, should we be asked to combine various unique elements in order to get total possibilities? Like if I told you I have 3 kinds of bread, 3 kinds of meat, 2 kinds of cheese, how many different sandwiches are there? All you have to do is, well, multiply. For more complicated scenarios, that is to say, taking a large set of objects and putting them in different orders, or taking a large set of objects and just picking them in a way in which the order in which they're selected doesn't matter, we always want to ask ourselves the question in our mental flowchart: does the order of the elements, does that matter? Is that material to us in this question? If the answer to that question is yes, the order matters, it is going to change the outcome, then that is what is referred to as a permutation, and we use the NPR equation. It is both a button in our calculator, and if you were to just like Google NPR, well, you would probably get sent to npr.org first, the radio station, but the second link will be the Wikipedia article to the permutation equation. This is not just in this pre-cal book, this is a much bigger, broader idea in statistics generally. If you were to ask yourself that question, does the order matter? And the answer to that is no. We're just picking groups. It doesn't matter that it's A, B, C, or B, C, A, or whatever. Then we use the combination equation, very similar, but it removes repetitions. In the specific case that you are doing a permutation type event, but there are repeated elements in that event, you are going to have to divide out those repetitions to decrease the total number of possibilities. And all you have to do is divide out by the number of repeated elements factorial, and that will remove all of the repetitions. I'll post the homework that goes with this section, and then tomorrow when we come in, we'll have a warm-up that uses permutations and combinations in an interesting way. And then we'll have the rest of the period to work on the homework together, because normally this is the hard part when it comes to learning about probabilities, like understanding why these work. So I want to make sure that we have at least one period in class together to go over that. Please do start the homework so that tomorrow, instead of talking about the easy ones, we can talk about the hard ones together. But yeah, best of luck to y'all, and I'll see you tomorrow.
All right. See you, Mr. Robinson.
Yep, y'all have a
Okay.
nice day.